So we're going to look at trigonometric functions and their derivatives. If we look at the very first graph, this is a function of sine of x. Now from this point forward, everything that we talk about in terms of sine, cosine, tangent, cotangent, cosecant, and secant, we are no longer talking in degrees. If we look at the original function in red of sine of x, we can find its derivative by analyzing the actual graph first. Key points, again, where is your slope going to be 0? So there's a couple of spots where the tangent where the slope is actually 0. In those cases, those translate to zeros on the graph. And there you go. So, as you can see, we've got 4 zeros based on a slope of 0 on the graph. If we analyze the actual graph itself, we can see our transition points also. We can also see when it's increasing, decreasing, decreasing. So when we have negative slope versus positive slope, and that will also help us estimate our actual graph. Points where it changes concave up versus concave down occur here, here, and here. Those will be our slope of positive 1, negative 1 in this particular case. So in this case here, we'd have negative 1, this case here, 1s, in this case here, negative 1. The reason for that, positive slope of 1, positive slope of 1. Negative slope here, negative 1 at the transition, negative 1 there. So you will then get the graph that looks like this. Which, if you take a look at it, it looks identical to the cosine graph that we have down below here. That's the cosine graph. This one looks identical to that cosine graph. So the derivative of f of x is equal to cos of x. If we analyze the other graph, the cosine x of graph, we can also see that it's very similar. It also has a few points where we have a tangent of 0. We can translate those onto the graph, zeros, zeros, zeros. We also have our inflection points where it goes from concave down to concave up. The slopes of these points here will also be 1. So, again, if we analyze, increasing, decreasing, increasing, so that we know that now, if I start here, let's start at the 0, I am decreasing, so I'm going to get to negative 1, and here I am increasing, I have positive slope, positive 1, and this portion here I'm increasing, so at this inflection point I would be positive 1. At this one here I'm decreasing, so I have a slope of negative 1. Now, if you take a look at this graph and compare it to the sine and the cosine graph, it's very similar to the, except it's a reflection over the line y equals x. So our derivative of this function, actually why don't we just call it g, so it's derivative of g of x is a negative sine of x. Now the remaining trigonometric functions can all be figured out just by using the sine and the cosine functions. If we were to look at the derivative with respect to x of tan of x, well, tan of x is the same thing as sine over cos. So technically, we're taking the quotient rule in this case. And we would then use our quotient rule and simplify it down. Now, in this class, there is a proof in the textbook. If you'd like to look through it, it is doable. You should have all the skills to do so. This is a good exercise to try. When you use the quotient rule on this one, it actually works down to being 1 over cos squared. Squared is the same thing as secant squared. If we also look at all the remaining cosecant, secant, and cotangent, we can also find them just by using their identities as well. And all of these are based on the fact that secant can be written as the derivative with respect to x of 1 over cos of x. This one is the derivative with respect to x of 1 over sine of x. And this one would be the derivative with respect to x of cos over x, cos x over sine of x. All of them use the identities to simplify down. So, the proofs are in the textbook. By all means, you can go through. They all use either the quotient rule or they can use the product rule, depending on how you look at it. And the next main part of this unit is learning how to apply them and to evaluate at particular values. So now we're going to be looking at how the product rule and the quotient rule with the sine and cosines in the function is quite useful. When we had two polynomials multiplied by each other and we were looking at the product rule, we could distribute out and just use the power rule. Now that we have the tangents involved in the terms of the product, we have to really actually use the product rule for the entire problem. Now in this one, we know that when we have a function like this, x times tan of x, this would be our first function that we're looking at. This would be our second function. Those are the two that are being multiplied together. So you can go x times the derivative with respect to x of tan x plus the derivative of with respect to x of x times by tan of x. Now we just talked about the tan of x as to what it is in terms of the identity. Derivative of tan of x is secant squared of x. So we'd have x secant squared of x plus the derivative of 1 is, or x is 1. So we would just have tan x. Another example is when we take the derivative of secant theta over theta, and we're taking the derivative with respect to theta. This one's going to use our quotient rule because we have a numerator and a denominator. Again, if you want to call them f and g. So ultimately you take your numerator and then we times it by the derivative with respect to theta of secant theta. Then we take the difference of the derivative of theta times by just secant theta. And that whole thing is over top of theta squared. So you do need to know what the derivative of secant theta is. Secant theta is secant theta tan theta. So we'd have theta times secant theta tan of theta minus secant theta. The derivative of theta with respect to theta is just 1. And that whole thing is over theta squared. Now, if you can simplify, it's ideal to do that. In this case, we could factor out a secant theta, theta tan theta minus 1. There are no other identities or anything else we can factor out, so that's fine.